In this example, we're going to calculate the hydrostatic force of a curved surface. Okay? We're given a reservoir which is 13 feet deep, and it's got a circular gate with a radius of 6 feet. Okay? The width of the reservoir and of the gate is 2 feet. That would be going into the board. And what we're trying to figure out are what the horizontal and vertical reactions would be. Now recall that when we solved an earlier problem with hydrostatic forces on a plane surface, the reaction that we were trying to solve for was actually perpendicular to the gate itself. But with curved surfaces, what we do is we actually looked at the projections and we figure out the components of those reactions instead. So we figure out what the horizontal force reaction is going to be and the vertical force reaction. We start, as we always do, with a free body diagram. And what I'm looking at specifically is a free body diagram of the gate. Okay, so I have a quarter circle, and then I have a control volume of water acting on that gate. Okay, and I'm going to go ahead and draw again the reactions that I'm solving for, the horizontal reaction and the vertical reaction. Okay, the horizontal reaction is going to be related to this horizontal force Fx. And what Fx is again, it's the hydrostatic force acting on a plane. With curved surfaces, we don't necessarily look at the actual surface itself, but we look at projections. So the idea is that if you were diving and you were looking at this gate from this perspective, looking towards your right, all you would see is a rectangular gate that's 6 feet high by 2 feet wide. Okay? And that's the force we'll be looking at. Now on the vertical side, there's a couple pieces. First of all, we have the weight of the water, okay, that's located below the gate that we have to consider. And then the other force we're considering is the force that's pushing up on the gate. Okay, and this you can imagine as, say we didn't have this gate. Say all we had was the reservoir that was 13 feet deep. Okay, at a depth of 13 feet, there's a pressure pushing up. That pressure pushing up over this area represents this force Fy. So using those, looking at my free body diagram, if I write the equations in the x direction, we see that Fx is equal to Fh. Likewise, in the y direction, okay, the reaction force Fv, okay, in the vertical direction would be equal to Fy, which is going up, minus the weight. So what we're going to do now is we're going to actually solve for these individual components. We're going to solve for Fx, we're going to solve for Fy, and solve for the weight. Okay, let's go ahead and start with the horizontal reaction. Okay. So as we know, Fx is equal to Fh. Okay. The equation for this is going to be very similar to what we've done in the past. It's specific weight of the water times the area, and I'm going to put a subscript for P for projection, times the depth of the centroid. Okay. Now, it's very similar to the formula that we've used for hydrostatic forces on planes. The only difference is now we're looking at the area of the projection. So the area of the projection in this case is we have a gate that's 6 feet tall by 2 feet wide. So that gives us an area of 12 square feet. Okay. The depth of the centroid, what we're looking at is specifically, here's the centroid of this rectangular gate. I'm sorry, of this quarter circle gate. But when we view it as a rectangular gate. And it has a depth of, let's see, this depth here would be 13 minus 6, right? So we have 7 feet. Plus, and there would be half. So this is that depth that we're solving for. It would be half of the 6 feet. So 6 feet over 2. So we have a depth of 10 feet. Okay? And so if I solve that, I'm going to solve that over here where I have a little more space. So when I solve for this, I'm going to get that the horizontal force is equal to, I'm going to have gamma, which is 62.4 pounds per cubic foot. Okay, we have an area of 12, and then we have a depth of 10. Okay, and this gives me a total horizontal force of 74.88 pounds. So there's the first part of this problem is solving for the horizontal reaction. Okay. Now I'm going to use the rest of the space here to calculate for the vertical reaction. All right. So in this particular case, again, looking at the free body diagram, we're considering this upward force. It's pushing up on the gate Fy. We're looking at the downward force from the weight of the water, W. We'll start with the weight. Okay. The weight is going to be the volume of this body of water. So I'll use this for my symbol for volume, and then I'll just show this as a quarter circle times the gamma of water. Okay. Now to get the volume of this quarter circle, we're going to look at the area. The area of a circle is pi r squared. Our r is 6 feet. And again, we have a quarter circle, so we'll have a quarter of that area. All right. And then let's see what we've got. We've got 2 feet. Was it 2 feet going into it? Okay, all this represents the volume term. And then we have, of course, the weight of water, which is 62.4 pounds per cubic foot. And again, I've been using this value. I've used it in the previous part. It's a rule of thumb value. We didn't have any specific temperature or anything of the water, so we just used the rule of thumb value. Okay. When I solve for this, I get that the weight is equal to 3528.6 pounds. Okay. So that's the weight of the water. So that's the first piece. Now we have to calculate this upward force. Okay. And when I do this, I'm going to think about this from a similar perspective. In my mind, I'm envisioning something like this, where I have a column of water. Okay, again, I'm not thinking necessarily about the quarter circle. I'm just envisioning if I have a reservoir that's 13 feet deep, acting on the surface of this soil, you have 13 feet of head. Okay, and that's acting over, which is a pressure, right? If we take gamma times that depth, that's a pressure, and that's acting over the area of this gate, which is 6 feet wide by 2 feet going into the board. So we'll go ahead and set that up. The first volume, so we have it's 13 feet deep. Okay, the width of the gate, to get this area is 6 feet. Okay, it's going 2 feet into the board. Okay, and then the gamma term, of course, will be the 62.4 pounds per cubic foot. Okay, this gives us a value of, let's see, it's going to be 9734.4 pounds. Okay, so we have these two pieces. Okay, and then going back to our free body diagram to solve for the final answer, we're just going to be taking the difference between those two. So we have 9734.4 minus the 3528.6. If I take the difference between the Fy and the weight, I get 6205.8 pounds as my final answer. Okay, so I solved for the horizontal reaction and the vertical reaction, and that's how we solve it for these curved surface problems. We don't, again, look at the force perpendicular to the object itself, but their actual projections. And that concludes our example.